Hello, friends. Today we're going to take a look at reviewing AP Physics C Unit 2 Mechanics. This is usually referred to the way that we construct it, at least the way that I've put the unit together, is dynamics. So basically, Newton's laws, um, primarily Newton's second law. So let's take a look. First of all, whenever you think of a force, I want you to think of a force as an interaction between two objects. Don't think of it as a push or a pull. It could be too abstract. The other thing that happens is that when people are thinking about forces, they just start adding kind of like random forces that are kind of made up. Whenever there's a force, what that means is that there are two objects, two physical objects that are interacting with each other, right? At least in Newtonian mechanics, this is how we deal with it. Um, it is a vector, so the direction matters, and we represent it like other vectors with an arrow, and that tells us the magnitude and the direction of the force. Right. Now, if it's two objects that are interacting, how do we know the direction? Because they're pushing or pulling out each other. What we do is we talk about the force with respect to, this is the force acting on this object. So we're looking at one object at a time and then looking at the interactions of other objects with that one object. Right. So we kind of zero in. Newton's second law, right? It's the kind of the basis, the whole foundation of physics. F net equals ma. Again, F net. So we're adding up all those interactions acting on that one object, and then that is equal to the mass of that object times the acceleration. Newton's first law is really just Newton's first law when it's in equilibrium, right? In other words, when F net equals zero, and that's when A equals zero. Oftentimes it's expressed, right? Objects in motion stay in motion, objects at rest stay at rest. That needs a lot of clarification, right? Because there could be lots of forces acting on an object, and yet it's remaining at rest. The whole idea is if the net force is zero, then the acceleration is zero. The velocity is constant. Anytime you hear a constant velocity, you've got to think equilibrium, net force is zero, etc. Newton's third law is just telling us that the interaction between two objects, it's the same magnitude of force between them, and they're just in opposite directions. If you think of a force as an interaction between two objects, the Newton's third law is kind of implied, right? You can't have one object interacting with the other and the other not interacting back on that other one. The phrase, the expression, equal and opposite, when objects interact, they exert. Or no, sorry, the expression I don't like is that for every equal action, there's an equal and opposite reaction. It makes it sound like there's an action reaction type thing. Instead, it's just one single interaction between the two objects. All right, so kinds of forces, and I get in the way I've constructed my units, I get into uh, some of these in other units, right? But so we have here the gravitational force, right? The universal gravitation between any two objects near the surface of the Earth. F little g, right, is mg. G is 9.8. Most of the time, I personally like to round that to 10 meters per second squared instead of 9.8. On the test, if you're doing calculations, may as well be safe and just do 9.8 on the AP test. That is the friction. Right? So the whole idea is that whenever there are two surfaces, there's some coefficient, there's some property of how locked those surfaces are with each other, right? How easily they're going to be able to slide against each other. And that's what mu represents. And then circular motion. I've got a couple examples here with circular motion. But the whole idea here is that we have a net force, a net centripetal force. So this could be one force. It could be a part of one force. It could also be a bunch of forces put together that add up to some net centripetal force. That's equal to mv squared over r. Acceleration is v squared over r. There's some different types of forces, and there are others that come up throughout the course. But for now, in Unit 2, one term that it's important to know is the equilibrant. The equilibrant is the thing that puts a body into equilibrium. So, for example, if there's an object, a random object that has a 5 Newton force on it, the equilibrant would be 5 Newtons in the opposite direction. So, in other words, right, it's the force that would make that thing in equilibrium, that would make the net force zero. Okay, force diagrams. This is big, big, big thing. Very important here. So what do? You create a circle, box, or dot. Very simple. It's not a sketch of the object. You're not. It's not an art class. Circle, box, or dot. I personally like boxes because then if you have more than one force, you can draw them like on the same surface. But boxes or dots work. The force. Then you draw the forces as vectors. The tail connects to the thing that you drew, the circle, box, or dot. You can have the tails coming from the center or just touching the object, but they have to touch the object when you draw them. So for example, if this is your object and you draw a force like this is no good. Don't do that. This force has to connect to the box, right? Or go all the way to the center. Some people do that as well. Right? Again, personally, I like to just go to the surface because then if there's another force there, I can add it like that. Um, and then all forces are clearly labeled. If you're dealing with two dimensions, then what you first you draw the what we call the raw force diagram. Uh, then you show separately the direction of the acceleration, and then you draw a separate force diagram where all the forces are resolved to parallel and perpendicular to the acceleration. Here's an example. Conical pendulum. So that's like, a ball on the end of a string, but instead of just swinging back and forth, it's swinging in a horizontal circle. Uh, so if this is the situation, right, it's at an angle theta from the vertical, and it's going around like this. So at this point, draw the force diagram when it's on this point. Okay, so first of all, here's the raw force diagram. What are the objects that are interacting with this ball? Um, and again, think in terms of the objects, because it would be too easy to look at this and just be like, oh, there's a force this way, applied force that way. No, don't do that, right? So there's the string and there's the earth. That's it, two objects. So here you're going to have the tension in the string this way, and you've got the earth pulling down this way. What's the direction of the acceleration? Well, it's moving around in a circle here, which means that when it's over here on the right, the acceleration is directly to the left, horizontal. So I draw the acceleration this way. Now I know when I break this up into its components, I'm going to make everything parallel and perpendicular to the acceleration because I need that in order to set up Newton's second laws like I did here, right? So now the way this angle turns out, right, the vertical component here is cosine, or it should be cosine. I wrote it wrong. And because when I draw this angle this way, this is where theta is. So ft cosine theta here, and then this is ft sine theta here. That's the horizontal component. Now, from this, once I fix sine and cosine, uh, so now I just write Newton's second law horizontal and vertical, right? Newton's second law parallel to the acceleration. So that's ft sine theta. And then vertically, there's no vertical acceleration, right? And so here, ft cosine theta, get that right, ft cosine theta minus fg is equal to 0, right? That's what the acceleration is. So it's in vertical equilibrium and horizontally it's accelerating this way. Again, since it's circular motion, I could substitute v squared over r. It all depends on what my next step is going to be, what I'm going to plug in, what I'm going to solve for, etc. Okay. So, I mean, like one thing you could do if you had to, you could use this equation to solve for ft. If you know the mass of the object, you can find ft. And then if you know what maybe they ask you to find ft's and you get that from this one. Or maybe they want you to find the velocity for it to remain at that particular angle. So you find ft, plug ft in here, etc. You go from there. Lots of different things to do, but this is the whole key, right? The reason the force diagrams are so important is because Newton's second law, which is the key to solving everything else, comes directly out of. It's just like an equation representation of the force diagram. Okay, so now when you're creating the force diagrams and you're writing out Newton's second law, it's important to realize that any objects that are moving together that have the same acceleration can be considered a single object. So, for example, the Atwood machine, like this, Oftentimes, if you're going to solve for the acceleration, people will draw two separate force diagrams, one for this mass, one for this mass, and you've got the tension, and then you end up having to solve for the tension and like set them equal to each other. It ends up getting a little bit complicated, and you can do it. But in the end, when you substitute everything together, you just end up with this. But check this out. These two masses are connected and they do move with the same acceleration. That means that uh, if, you know, I can choose kind of like this direction as the acceleration, right? So this one moving up, this one moving down. If I choose that as the same, so I can treat them as one system. System thinking is super important, right? So what's my system? If I take both masses as the system, then the tension is internal to that system. Newton's second law only applies to external forces. So what are the external forces here? Well, there are only two, little mg and big mg. So when I write the net force equals ma, m total, write that there. So what are the forces? Well, it's just these two, right? This one is pulling in the direction of the acceleration. This one's pulling opposite the direction of the acceleration. So I write mg minus mg equals, both masses are the system, so m plus m times a. And now it's really simple to solve and get the Atwood machine formula, you could say. You get that. And it all just comes out of forming one equation. You put it to, and then you just solve for what you need. So pay attention to systems, and that, because that will also dictate how you can set up Newton's second law. And sometimes you can manipulate things to make it simpler to solve. Here's an example involving friction. Okay, so imagine we've got a situation where there's a block or something that's on a surface and it's being pulled with a rope, 20 newtons at 30 degrees to the horizontal. Okay, well, if it's on a surface, it's being pulled. Oh yeah, and mu k, the coefficient of kinetic friction is zero point 0.2. So I want to know, what is the net force? Well, there's going to be friction to the left. There's a normal force up, earth force down. But here's the key. Because there's an upward component here to the um, tension force, the normal force is not equal to the earth force. It's going to be less. And so let me zoom in here. So now I have that, right, this force diagram, and I know the acceleration is going to be this way based on this situation, what I've described so far. So now I go over, break this up. Okay, I know that I don't know what the friction force is going to be. I've taken the tension force and resolved it, parallel and perpendicular, like this. And so ft sine theta, so ft is 20 and sine of theta, sine of 30 degrees is just 1/2. So this is 10 newtons. And then ft cosine theta, so 20 times cosine of theta is going to be 17.3 newtons. Always good to know your 30, 60, 90, right? So root 3 over 2 times 20, etc. Um, and so I know the friction force now is going to be less than 17.3 because it's accelerating to the right. But in order to find out what the friction force is, I need to know the normal force. Well, the normal force is going to be the earth force minus ft sine theta times sine 30, right? Because these two upward forces together have to add up to this one. So fe, so 30, here again, 3, so I'm multiplying by 10. I'm using g as 10. Minus these 10 newtons from the tension force. And so this ends up being 20 newtons. Okay, so the normal force is 20 newtons. So the friction force is mu k times Fn, which is going to be 0.2 times 20. So that's going to be 4 newtons. Okay, the net force then, it's supposed to be a sigma. So sigma F equals 17.3, right? That's this, minus 4 newtons. So it's 13.3 newtons horizontally. There's no vertical net force. It's in equilibrium that way. Okay, so again, what did I do? Start with this raw force diagram. Acceleration's this way. Break this up, and then I'm just using Newton's laws. So again, vertically it's in equilibrium. The acceleration is zero. So these have to add up with these, right? So you get zero when you add all these verticals together, and then this plus this equals the net force. Some reminders for circular motion too. I did the example of the what do you call it? The conical pendulum as an example for setting it up, right? And again, the key idea that the centripetal force, we call it centripetal force, but really I tell my students never put centripetal force on a force diagram. Always pay attention to the uh, the raw forces, because even like for example, with the conical pendulum, there is no centripetal force. There's no force on here, certainly on this one, that you could put. Some students will just add centripetal force here, but you can't do that, right? Because the centripetal force is actually just a component of one of the raw forces. Sometimes it'll be more than one force, they add up, or it's a component of this and another thing altogether. The centripetal force is always a net force. Treat it that way, and I wouldn't even put it on the force diagram. But then don't forget, right? The velocity, something moving a circle, 2 pi r over t. Capital T is the period, r is the radius of the circle, or 2 pi r f. F is frequency, and frequency, 1 over the frequency is the period. And don't forget the centripetal acceleration formula, v squared over r. Okay, those are the basics. A couple of examples. Unit 2, dynamics, is basically force diagrams and Newton's second law. That's kind of the whole thing. And then just some different ways that objects interact with one another. So thanks for watching. Don't forget to like and subscribe.